So the topic of today's discussion will be pulsating MMF due to single phase winding. So this term pulsating MMF you will encounter when you study single phase induction motor. So what is the meaning of this word pulsating MMF? Pulsating means which is changing with time. The magnitude or the amplitude of that quantity is getting changed as the time passes on. So pulsating MMF means that it is a MMF, that is magnetomotive force. The magnitude of this magnetomotive force is going to be a function of time. That means the value of the MMF, the magnitude of the MMF is going to change with respect to time. So that thing is usually expressed by the term pulsating MMF. So pulsating MMF means MMF which is going to change its magnitude with time. Now, to be precise or to be accurate, we should not only use the word pulsating, rather we should say that the MMF in the air gap of a single phase induction motor is a function of both space and time. That means it is a function of both space angle as well as it is a function of time. So we will definitely try to derive that particular statement that MMF in the air gap of a single phase induction motor is going to be stationary and pulsating, and besides that we will also find out that the MMF in the air gap, or you take any arbitrary point you take in the air gap of the induction of the single phase induction motor, you will find that the MMF at that arbitrary point in the air gap is a function of both space angle as well as time. So at now it may not be fully understood by you these terms, that the MMF in the air gap of a single phase induction motor is a function of both space and time. So I will come to that and I will elaborate all the steps which are needed in order to realize the meaning of these words, that is space angle and that thing. But yes, before I start, I want to again, what should I say, mention a very important thing, is that when I am saying that the MMF in the air gap of a single phase induction motor is stationary and pulsating, here I have made one assumption which I have not stated explicitly. So what is the assumption which I have made? I have made the assumption that the single phase induction motor is having only one winding, that is the main winding. So usually you will find that in a single phase induction motor there are two sets of winding. One winding is known by the name of main winding and another winding is known by the name of auxiliary winding. Now you will find that the main winding is referred by the name of running winding and auxiliary winding is referred by the name of starting winding. So when I have said that particular line, that air gap MMF or the MMF in the air gap of a single phase induction motor is stationary and pulsating, so there I have made that assumption that the single phase induction motor is having only one winding energized. That means only the main winding is energized. Even though if there can be auxiliary winding, that auxiliary winding is not energized. So this point is very important, otherwise that will lead to a confusion. The thing is that whenever we are saying that MMF in the air gap of a single phase induction motor is stationary and pulsating, we are making assumption, although not said explicitly, but we are assuming that only one winding, I mean to say only the main winding is energized, whereas the other set of winding, that is auxiliary winding, either it is not there or even if it is there, it is not energized. So it is somewhat better to use the phrase that MMF in the air gap of a single phase, single winding induction motor is stationary and pulsating. So when we use the word single phase, single winding induction motor, so single phase, single winding induction motor implies that only one winding, that is the main winding, is energized. The other winding, that is the auxiliary winding or the starting winding, is not energized or it is not there at all. Now, let us now make an effort to realize the meanings of these terms which we have said in the beginning, that is the space angle. So now we will start with the cross-sectional view of a single-phase induction motor. So that cross-sectional view of the single-phase induction motor you can view over here. You may follow the mouse pointer, please. So this is the cross-sectional view of a single-phase induction motor. So you can see that there are 6 number of slots which are there on the stator core periphery. However, let me state that usually 2/3 of the stator periphery, let me again say, usually 2/3, that means 2/3 part of the stator periphery is occupied by the main winding, and the remaining 1/3 of the stator periphery is occupied by the auxiliary winding. So in any case, this stator core periphery should have both slot and teeth, which should be uniformly distributed throughout the stator core periphery. But I have just indicated only 6 number of slots in the stator core periphery, just to avoid the labor and time. That's it. But we should keep in our mind that the entire stator core periphery is uniformly slotted. However, even though the entire stator core periphery is uniformly slotted, only two-third of the total number of slots will be occupied by the main winding, and the remaining 1/3 of the slots will be occupied by the auxiliary winding. Let's say if there are 24 number of slots, so 2/3 of 24 is 16. So 16 slots will be occupied by the main winding, and the remaining 8 slots will be occupied by the auxiliary winding. Now let us just find it over here that on the stator core periphery we can view that there are 3 coils, and the coils are named as A1 A1 dash, A2 A2 dash, and A3 A3 dash. Now these 3 coils, A1 A1 dash, A2 A2 dash, and A3 A3 dash, these are multi-turn coils. Multi-turn coils, you can view the picture over here at the left hand side bottom. This multi-turn coil will have n number of turns, although it is one single coil. So don't think that it is n number of coils. It is only one coil, single coil, but this one single coil is having n number of turns, so it is known as multi-turn coil. So all the 3 coils, A1 A1 dash, A2 A2 dash, and A3 A3 dash, these 3 coils are multi-turn coils having n number of turns. So obviously in the slots you will have n number of conductors, because this being a multi-turn coil having n number of turns on each coil side, so there are n number of turns on each coil side. So you will have n number of conductors. You will have n number of conductors on each coil side. So that's why in coil side A1, the slot which is placed, or the slot which is housing the coil side A1, the slot which is housing the coil side A1 will have n number of conductors. Likewise, the slot which is housing the coil side A2 will have n number of conductors. So this way we can say that there are n number of conductors in each of the 6 number of slots which we can see over here. Now what is our next step? Our next step is that we need to find out that what will be the magnetic axis or the resultant MMF axis due to the combined action of these 3 coils, because these 3 coils, A1 A1 dash, A2 A2 dash, and A3 A3 dash, they will be connected in series. So if they are connected in series, so they will carry the same current. Not only that, all the 3 coils is having the same number of turns. All of them are n turns coil. That means all the coils, all the 3 coils are having n number of turns, and since they are connected in series, so they are carrying the same current. So you see, the MMF which is developed by the coil A1 A1 dash and the MMF which is developed by the coil A2 A2 dash, they will be equal in magnitude. But what is the difference? The difference will be with respect to the line of action or the orientation. So you please follow the mouse pointer. You may find that this is the plane. This is the plane which is containing the coil side A1 A1 dash. Now coil side A1 is indicated to carry cross current and coil side A1 dash is indicated to carry dot current. So now if you apply that right hand grip rule, you will find that the magnetic axis of the coil A1 A1 dash is acting along this direction, which is indicated by this red arrow. So this is the magnetic axis of the coil A1 A1 dash. Now the magnitude of the MMF will be, no doubt, it will be N into I. That is, all the coils are having same number of turns N and they are connected in series, so they are carrying the same current I. So magnitude of MMF which is developed by each of the three coils are equal, but what is the difference? The difference lies in their orientation in space. The orientation in space means the magnetic axis of the three coils, they will be separated in space. They will not be aligned in space. They will be separated in space. So you can again look at this particular diagram. You may follow the mouse pointer, please. So you see the magnetic axis of coil A2 A2 dash, you will be horizontal like this. It is shown by the green arrow. So magnetic axis of the coil A2 A2 dash will be horizontal and it is indicated by this green arrow. Likewise, the magnetic axis or the MMF axis for the coil A3 A3 dash will be like this, which is shown by this blue color arrow. So what we find, that the magnetic axis of the three coils, that is A1 A1 dash, then A2 A2 dash, then A3 A3 dash, the magnetic axis of the three coils, they are separated in space. They are not aligned. This can be easily viewed if you just have a look regarding the magnetic axis of the coil A1 A1 dash, which is shown by the red arrow. Likewise, the magnetic axis of the coil A2 A2 dash, which is shown by the green arrow, and magnetic axis of the coil A3 A3 dash, which is shown by the blue arrow. So you see, the magnetic axis of the three coils, they are not aligned, rather they are separated in space. Their orientation is not aligned in space, they are separated in space. So this is because why at all the magnetic axis of the three coils are separated in space? This is because the distribution of the coils. This is because the distribution of the coils along the stator core periphery, isn't it? Now, what can we always do, is that we can resolve the MMF of the coil A1 A1 dash into two components. So you can follow the mouse pointer, please. This brown arrow is representing the horizontal component and this black arrow is representing the vertical component of the MMF for coil A1 A1 dash, which is shown by this red arrow. So this red arrow is indicating the magnetic axis or the MMF axis for the coil A1 A1 dash. So this MMF of the coil A1 A1 dash, shown by the red arrow, is resolved into two components. One is horizontal component, which is shown by the brown arrow, and another is the vertical component, which is shown by the black arrow. Now for the coil A2 A2 dash, you will see that the magnetic axis of coil A2 A2 dash is itself on its own horizontal, because the coils A2 A2 dash, they are placed in a vertical position. So the magnetic axis of the coil A2 A2 dash is horizontal. So it will have only one component, that is the horizontal component. There won't be any vertical component. Now let us switch our attention to the coil A3 A3 dash. So for coil A3 A3 dash, the magnetic axis is acting along this blue line, which is perpendicular to the plane which is containing the coil side A3 A3 dash. So this blue line is the orientation of the magnetic axis or the MMF axis for the coil A3 A3 dash. So we can again resolve this into two components. One is horizontal component, which is indicated by this brown arrow. You may follow the mouse pointer, please. So this is the horizontal component of the MMF for the coil A3 A3 dash, and this black arrow is the vertical component, This black arrow is the vertical component of the MMF for the coil A3, A3 dash. So now what you can do, you can superpose them, because when we have indicated these things, the magnetic axis of the three coils separately, we are assuming that when one coil is carrying current, the remaining two coils are not carrying any current. So that way we have drawn the magnetic axis for the three coils in these three diagrams. Now when you superpose, that means what? Actually all the three coils, they are going to carry current at the same time because they are connected in series. So if you superpose this, what do you find? You will find that the vertical component of the MMF, the vertical component of the MMF for coil A1, A1 dash, and the vertical component of MMF for coil A3, A3 dash, they will cancel each other, because one is vertically downwards. I mean to say the vertical component of MMF for coil A1, A1 dash is vertically downwards, whereas the vertical component of MMF for coil A3, A3 dash is vertically upwards. So these two components, the vertical components of MMF for coil A1, A1 dash and A3, A3 dash, they will cancel each other. So ultimately we are having the horizontal component. So the resultant magnetic axis or the resultant MMF axis, due to the combined action of these three coils together, will be given by this brown arrow axis, which is horizontal. You may follow the mouse pointer, please. So this is the magnetic axis, which is known as the resultant magnetic axis or the resultant MMF axis, due to the combined action of the three coils which are carrying current together. So now, once we have made ourselves convinced with this magnetic axis determination of the three coils, so we can now switch our attention to the nature of the MMF distribution in the air gap. So what do you find here? That developed view of the stator core and rotor core are indicated in the diagram. That means this one, you may follow the mouse pointer. So this is the stator core and this is the rotor core. Now this particular thing is the cross sectional view, isn't it? So this cross sectional view is indicating that the magnetic lines of flux which are plotted, they are going to result into how many number of poles? They are going to result into two number of poles, because you see at the stator core, where the point B is there, you may follow the mouse pointer, please. So at stator core where the point B is there, the magnetic lines of flux are leaving the stator core. So you will have a north pole over here at point B on the stator core. Whereas at point A on the stator core, you will see that at point A on the stator core, you will see that magnetic lines of flux are entering. So this will be your south pole. So we see that there are only two poles which are going to develop on the stator core. So now this is actually going to prove an advantage for us. That is that if we analyze the MMF distribution of a coil, which is for two number of poles, then the advantage we have is that we are spared from the confusion of electrical degree and mechanical degree, because when the number of poles are two, then theta electrical and theta mechanical are one and the same. So we are spared from that confusion. So that is the advantage we get if we make our analysis taking two number of poles. Now what do you find here is that the magnetic axis of these three coils, it is directed in the direction from point B to point A. So now what we have done, we have made a cut on the stator core. We have made a cut on the stator core. We have made a cut on the stator core at point B. This is the line. You may follow the mouse pointer, please. So this is the line along which the stator core is being cut out, only at this point, along this line only. You may follow the mouse pointer. Then we are stretching it like this. So if you stretch it like this, you will have this developed view. So you see point B will be over here and point A will be over here, and again you will have point B, that is this point is again point B, because the whole thing is actually round. So if you again wrap and curl the stator core, then this point B on the right side of the stator core and this point B on the left side of the stator core, they should get coincide. So that is the basic idea of writing B on both the edges of the stator core. One on the left edge of the stator core, another point B is written on the right edge of the stator core, because this thing, when it is going to be curled back into the round shape, so these 2 points on the left and right corner of the stator core, that is point B, they will coincide. Now, once we have done with this, let us try to justify that why is it that all the three coil sides, namely A1 dash, A2 dash and A3 dash, will carry dot current, and why it is like that all the three coil sides, namely A1, A2, A3, will carry cross current. Actually, this can be easily figured out if you just give a close look to this particular series connection of the coil. Please follow the mouse pointer. So if you connect these coils A1, A1 dash, A2, A2 dash and A3, A3 dash in series, and if you assume any particular direction of current flow, let's say we are taking this to be the direction of the current flow, so you will find that current carried by the coil side A1, coil side A2 and coil side A3 are in the same direction. So that is the reason we have put this dot marking for the coil side A1 dash, A2 dash and A3 dash, because when you are looking in this diagram, please follow the mouse pointer, when you are looking in this diagram, you see the direction of current carried by the coil side A1, coil side A2 and coil side A3 are in the same direction. So that's why we have indicated dot polarity of current for all the three coil sides, that is A1 dash, A2 dash and A3 dash. Now, similar argument can be placed for coil side A1, A2, A3. Now, what do you know is that when we have derived the nature of MMF distribution for a single full pitch coil having n number of turns, it was found to be rectangular in nature. But over here, we are having three coils. So what we do, we plot the nature of MMF variation assuming only one coil is carrying current at a time. So accordingly, we will have three graphs. So you can see there are three rectangular MMF distribution. So these three rectangular MMF distribution is corresponding to those three coils, which are named as A1 dash, A2 dash, which are named as A1 A1 dash, A2 A2 dash and A3 A3 dash. So what we have done, we are assuming that only coil side A1 A1 dash is carrying current. So at that time A2 A2 dash and A3 A3 dash, they are not carrying any current. So what is the nature of MMF variation? Since only one coil is carrying current, that is A1 A1 dash, so the nature of MMF variation will be rectangular in nature. So this is the MMF variation. Likewise, in the second case, we will assume that only coil A2 A2 dash is carrying current. The other two coils, that is A1 A1 dash and A3 A3 dash, they are not carrying any current. Only coil A2 A2 dash is carrying current. So in that case, the middle one, please follow the mouse pointer. This is the MMF variation due to the current carried by the coil side A2 A2 dash. So this is the MMF variation for current carried by the coil A2 A2 dash. Now in the third case, we will make the similar assumption that only coil side A3 A3 dash is carrying current. Only coil A3 A3 dash is carrying current, and remaining two coil A1 A1 dash and A2 A2 dash, they are not carrying any current. So in that case, please follow the mouse pointer. In that case, this is the MMF variation. This is the MMF variation when coil A3 A3 dash is carrying current. So now this is in accordance to the nature of MMF distribution which we have derived in our earlier class, where we have found that the MMF distribution for a single full pitch coil having n number of turns is actually rectangular in nature. So what was the magnitude? The magnitude was Ni by 2. That means this will be, this portion will be plus Ni by 2 and this lower portion will be minus Ni by 2. Likewise for the second coil, this portion, please follow the mouse pointer. So this portion is Ni by 2 and this portion is your minus Ni by 2. So if we superpose, because you see over here, we have only assumed that when one coil is carrying current, other two coils are not carrying current. But that is not the actual case. Actually, all the three coils are carrying current at the same time because they are connected in series. So what needs to be done? We need to apply the principle of superposition. So by applying that principle of superposition, we have simply added the ordinate. Ordinate means the y value, that is value along the y axis for the combined action. So what you do, this please follow the mouse pointer. So this portion is minus ni by 2. Again, this is also minus ni by 2. This is also minus ni by 2. So in particular this block, it will be minus 3 by 2 ni by 2. Minus 3 by 2 into ni. Over here in this particular block, this plus ni by 2 and minus ni by 2 will cancel. So you are living with minus ni by 2. So you have minus ni by 2. So in this way, you simply add the MMF in each of the block. Block means I want to say the slot pitches. This can be more precisely termed as the slot pitch. Slot pitch means you consider the distance between the center of the slot A1 dash and center of the slot A2 dash. So in this portion between the center of the slot A1 dash and center of the slot A2 dash, you just go on adding the MMF due to the 3 coils. So that will be the resultant MMF. Likewise, you add the MMF between these two slots, that is center of the slot A2 dash and center of the slot A3 dash. So you go on adding the MMF for the 3 coils between these two regions, that is center of the slot A2 dash and center of the slot A3 dash. So you will find the resultant MMF. So in this way, if you go on adding the ordinate, that is the y-axis value along the y-axis, you just add the MMF due to all the 3 coils along the y-axis. So you get the resultant MMF distribution when all the 3 coils are carrying current together. That means the combined action of the 3 coils. So what do you find? That it is actually a stepped MMF waveform. But this stepped MMF waveform can be approximated by a trapezoidal MMF waveform. So what is the justification we can give? What justification we can give for approximating the stepped MMF waveform by a trapezoidal MMF waveform? The only justification which we can provide is that the width of this slot pitch, that is the distance between the center of the slot A1 dash and center of the slot A2 dash. That means if you measure the distance between the center of the slot A1 dash and A2 dash, that distance is actually the slot pitch. So this slot pitch is very narrow. Although here it is shown to be wide, but actually this slot pitch is very narrow. So in that case, the width of this step will be also becoming very narrow. So that is justified by approximating this stepped MMF waveform by a trapezoidal MMF waveform. So what do you found out? That the nature of the MMF distribution along the air gap periphery, the nature of the MMF distribution, actually it is more appropriate to use the word space distribution of MMF. Space distribution of MMF along the air gap periphery for these 3 coils was actually found to be trapezoidal in nature. Now what is done, is that this trapezoidal MMF waveform is a periodic waveform. Of course it is a periodic waveform because this is a trapezoidal in nature. So this trapezoidal MMF waveform, which is periodic in nature, and it is also satisfying your Dirichlet's condition, it is amenable to Fourier series expansion. Amenable to Fourier series expansion means we can apply Fourier series expansion. We can apply Fourier series expansion to this trapezoidal MMF waveform. Now, what is actually going to happen if you apply the Fourier series expansion to this trapezoidal MMF waveform? It will happen that this trapezoidal MMF waveform will be represented as summation of large number of sinusoidal waveforms. That means the same trapezoidal MMF waveform effect will be obtained if you superpose large number of sine waves. That means I am adding the ordinate, that is the y-axis value for large number of sine waves. So if I add them, I should again return back, or I should again get back the trapezoidal nature of the MMF waveform. So by Fourier series expansion, we are actually expressing the trapezoidal MMF waveform. We are expressing the trapezoidal MMF waveform into as actually these are represented as nothing but the summation of large number of sine waves. Now, out of this large number of sine wave, that sine wave, out of this large number of sine waves, which when added together will give me back the trapezoidal MMF. So out of this large number of sine wave, that sine wave which is having the same time period, as well as the same zero crossing as that of this trapezoidal MMF waveform, will be termed as fundamental component, and the remaining sinusoidal wave forms will have a time period which is actually submultiple of the time period of the fundamental component. So what we do actually, is that we try to keep things simple, and simply ignore we simply ignore the existence of the harmonic MMF waveform, or your what should I say, space harmonic MMF waveform. So what we only take into consideration, we take into consideration only the fundamental component of the MMF waveform, the harmonic component, or the space harmonic component. The space harmonic component of MMF is simply ignored for simplicity. So what can we do actually? Although it is not shown in the diagram, but what you can think is that if we are only considering the fundamental component, if we are only considering the fundamental component of the sine wave, which will be obtained when we apply Fourier series expansion to this trapezoidal MMF distribution, so that fundamental component of sine wave is only considered, and the remaining harmonic components of MMF, or the space harmonic component of MMF, they are ignored. So this trapezoidal MMF waveform can be replaced by a sinusoidal MMF waveform, and the peak of that sinusoidal MMF waveform will happen along this axis, which is the MMF axis due to the coil. So it will have a positive peak. You may follow the mouse pointer, please. So this is the axis which is here written as MMF axis due to the coils. So along this axis, the positive peak of the sine wave, that is the sinusoidal MMF wave, the positive peak will happen along this axis, that is the MMF axis due to coils, and obviously along this axis it will have a negative peak. It will have a negative peak along this axis. Please follow the mouse pointer. It will have a negative peak along this axis. It will have a negative peak along this axis, whereas it will have a positive peak along this axis. So now what we can do is that once we have expressed the what should I say, once we have applied the Fourier series and expressed the trapezoidal MMF distribution by a summation of large number of sine wave, and after that we have simply ignored or neglected the harmonic MMF waveform, or the space harmonic MMF waveform were neglected, and only we are taking into consideration the fundamental MMF waveform. So what do you find? That fundamental MMF waveform is having its positive peak along this axis, which is passing between the center of slot A3 dash and A1, and it will have a negative peak which is passing between the center of the slot A3 and A1 dash. So you may follow the mouse pointer, please. Over here, between the center of the slot A3 and A1 dash, you will have the negative peak, and between the center of the slot A1 and A3 dash, that is at point A, you will have the positive peak. So positive peak is happening at point A on the stator core periphery, and negative peak is happening at point B on the stator core periphery. Now once we have said this, we can do one thing, is that we can define an angle which is theta, and this theta is actually known as the space angle. So theta is the space angle. So how do we define this angle theta, which is termed as the space angle? Actually it is a method or a convenient way of locating or pinpointing any point along the air gap periphery. For example, if this axis, which is passing between the center of the slot A1 and A3 dash, the axis which is passing between the center of the slot A1 and A3 dash, that is point A, the axis which is passing through point A. So if we define this to be our theta equal to 0, so this point B will be theta equals to 180 degree, because we are moving in the clockwise direction, and point B on the left pole tip, point B on the left tip of the stator core will be theta equals to minus 180 degree. Why minus 180 degree? Because we are moving in the anti-clockwise direction. So you just correlate the developed view as well as the cross-sectional view. So please follow the mouse pointer. You see this point A is chosen as the reference. So axis which is passing through this point A on the stator core is chosen as the reference. So this is our theta equal to 0 degree. Now we are taking the convention that if the movement is in the clockwise direction, theta will be positive, and if the movement is in the anti-clockwise direction, theta will be negative. So now this point A on the stator core, or a air gap, an air gap point, or point in the air gap which is in front of the point A will be defined by theta equal to 0 degree, because it is lying in this axis which is defined as theta equal to 0 degree. Likewise, a point in the air gap which is in front of A2, slot A2, so that will be defined by theta equal to 90 degree. If you take a point in the air gap which is in the front of the slot A2, that will be defined by theta equal to 90 degree. And obviously this point B will be defined by theta equal to 180 degree. Now if you move to the left side of the MMF axis, if you move to the left side of the MMF axis, that is if you move to the left of the point A, then you are moving in actually anti-clockwise direction. So these will be defined by theta having a negative value. So if you have a point which is in front of the slot A2 dash, so this point in the front of the slot A2 dash will be defined by theta equals to minus 90 degree. Why minus 90 degree? Because you are moving in the anti-clockwise direction. So in this way, what you can do is that you can simply locate or simply pinpoint any specific point in the air gap periphery by just knowing one value, and that is the value of the space angle theta. So by one parameter, that is your space angle theta, it is possible to pinpoint and locate accurately any point in the air gap periphery. So that is the purpose of defining this space angle theta. Now what we have seen, when we have expressed or decomposed this trapezoidal MMF into a number of sine wave, we have seen that the fundamental component of sine wave will be that component which is having the same time period as that of the trapezoidal MMF in this case. So that fundamental component will have a positive peak along the axis which is passing through point A. You may follow the mouse pointer. So along this axis the positive peak will be happening. So we can say that the MMF at point C in the air gap, which is theta degree away from the reference axis, will be given by nothing but m dash max into cos theta. So why we are saying that m dash max into cos theta? What is the justification for saying this? We are saying that MMF at point C is given by m dash max into cos theta. What is point C? Point C is a point in the air gap which is theta degree away from the reference axis which is passing through the point A on the stator core. That is theta equal to 0 degree is defined for this axis which is passing through the point A on the stator core. So you are taking a point C which is theta degree away, you are taking a point C which is theta degree away from this reference axis. So this value, the value of the MMF at point C in the air gap will be given by m dash max into cos theta. Why m dash max? Because m dash max is the peak value of the MMF. What is m dash max? M dash max is the peak value of MMF, at theta equal to 0 degree, that is along the MMF axis which is passing through point A. So what you can actually figure out is that if you move either to the right side or the left side of this MMF axis which is passing through point A on the stator core, the strength of the MMF will gradually decrease. Let me repeat once more. What I am saying is that the peak of the fundamental component of MMF, which is a sinusoidal wave, because we have neglected the space harmonic. So the peak of the fundamental component of the sine wave or sine MMF wave will be happening along this axis, which is passing through point A on the stator core. So if you move either to the right or to the left of this axis, which is passing through point A on the stator core, you will find that the magnitude of the MMF is going to gradually decrease, and obviously it will be zero at point which is in front of slot A2, as well as it will be zero at point which is in front of the slot A2 dash, because theta equals to minus 90 degree at a point which is in front of slot A2 dash, and theta equals to 90 degree at a point which is in front of slot A2. So cos 90 is 0, isn't it? And cos 0 is 1, that is maximum. So we say that the MMF distribution along the air gap periphery, the MMF distribution along the air gap periphery is cosinusoidal, and we are expressing that by this particular term m dash max into cos theta. So now this m dash max is the peak value of the MMF at the point A, that is when theta equal to 0 degree, and m dash max into cos theta, m dash max into cos theta is the value of MMF at point C, which is theta degree away from the MMF axis. Now this particular thing will let you realize, what it will let you realize, that MMF in the air gap periphery is actually a function of the space angle theta. MMF in the air gap periphery, the magnitude of MMF in the air gap periphery is a function of the space angle theta. As the value of theta changes, then the MMF at that point in the air gap will also change. This is shown by this expression m dash max cos theta. Now this particular thing was analyzed by making one assumption which I have not stated, although let me state what is that. You see, MMF, that is magnetomotive force, is going to depend both on the which it will depend both on current which is carried by the coil, that is I, as well as the number of turns of the coil. Now once you have placed the windings in the slot, the number of turns are not going to change. So n is a constant. Now let us focus our attention to the nature of current. So if the current carried by these three coil sides, A1, A1 dash, A2, A2 dash, and A3, A3 dash, if the current carried by these three coil sides is direct current, that means it is DC, in that case the strength of the current I is not going to change with time. So in that case, the height of this rectangular MMF waveform for each of the coils, or the height of this trapezoidal MMF waveform, this height is not going to change. Please follow the mouse pointer. This height of the trapezoidal MMF waveform is not going to change with time if the three coils are carrying DC. That means if they are carrying direct current, if the three coils are connected to a DC source, in that case the strength of the current is not going to change with time. So that means the height of this trapezoidal MMF waveform will not change with time. The height of this rectangular MMF waveform for each of the three coils is not going to change with time. So in that case, it is perfectly okay to state that MMF along the air gap periphery is a function of space if the coils are carrying direct current. That means the coils are connected to a DC source. Now let us think again very closely that what will be the nature of MMF in the air gap if the coils are carrying sinusoidal current. So please follow the mouse pointer. You may refer to the mouse pointer. So you see over here, these three coils are connected in series and they are connected to a sinusoidal voltage source. So the moment the coils are going to be connected to a sinusoidal voltage source, so they will carry sinusoidal current, which is given by Im sin omega t. So now the height of this trapezoidal MMF waveform is no longer constant with time. It will depend upon the magnitude of the current which is carried by a coil at that particular moment. Let's say if it is omega t equal to 30 degree, if the moment is omega t equals to 30 degree, then what is the value of sin 30? It is half. So in that case the magnitude of the current, is given by Im sin 30, that is Im by 2. Now, after some time later on, when it is omega t equal to 45 degree, in that case, the magnitude of the current carried by the coil will be Im sine 45 degree. That means Im by root 2. So what do you see? That as the time is going on passing, or as the time is changing, the magnitude of the current which is carried by the coils, they are also changing, because of the simple reason that the coils are now carrying sinusoidal current, because they are connected to a AC voltage source. So they will carry sinusoidal current, and obviously the strength of the current will change with time because it is sinusoidal in nature. So the MMF magnitude which is given by current into number of turns will also change with time. So in that case we say that the height of this trapezoidal MMF waveform or height of this rectangular MMF waveform is going to change with time also. So in that case, what do you say? That MMF along the air gap periphery, MMF along the air gap periphery is a function of both space angle, that is theta, as well as time. So this thing is going to be valid when we say that the MMF along the air gap periphery will be a function of both space angle theta and time. That will be valid if the coils are carrying sinusoidal current. But if the coils are not carrying sinusoidal current, if they are connected to some DC source, if they are carrying direct current, in that case the current magnitude is not changing with time. So in that way, in that way you can say that the MMF in the air gap periphery is a function of space angle theta only if they are carrying direct current, that is DC. But if they are carrying alternating current, in that case the magnitude of MMF in the air gap periphery will be a function of both space angle theta as well as it will be a function of time, that means sine omega t. So that is what is written here, that the value of m dash max, that is the maximum value of the sinusoidal MMF which is occurring along the MMF axis at point A, is given by m dash max. But this m dash max, that is the maximum value of MMF, is a function of both number of turns n and current I. Now if current I is DC, in that case value of m dash max is a constant. So you say that the MMF in the air gap periphery is only a function of space angle theta. But if I equals to Im sine omega t, that means if the coils are carrying sinusoidal current, in that case the magnitude of m dash max, is not gonna remain constant. Why? Because the magnitude of m dash max is a function of both number of turns and as well as the current which is carried by the coils. So if current is sinusoidal, in that case the value of that m dash max will itself change with time. So we say that MMF at point C is given by m max cos theta into sine omega t. So this particular term m max cos theta sine omega t is making you informed that MMF in the air gap periphery is a function of both space angle theta as well as time, that is it is dependent on sine omega t. And what is m max? M max is the maximum value of MMF at point A, that is which is passing through MMF axis of the coil at instant omega t equals to 90 degree. So that is a point you should not forget, because if you choose the axis which is passing through point A on the stator core, please follow the mouse pointer. If you choose this axis, so this axis is theta equal to 0, this axis is theta equal to 0 degree. So if you put theta equal to 0 degree, so cos 0 is 1, and this will be maximum, the MMF at this point, the MMF at point in the air gap which is in front of point A, this point will have maximum MMF at instant omega t equals to 90 degree, because when omega t equals to 90 degree, sine omega t is 1. So the value m max is obtained at the air gap which is in front of the point A on the stator core, and this will be m max only at which time instant? At time instant omega t equals to 90 degree, not otherwise, isn't it? So this particular thing is very important. So I will again start from here in my next class, if I am going to start with that double revolving field theory.